Okay, so this video is the second part. It's going to cover pages 2 and pages 3 of the notes for section 4.6. It's still the applications of growth and decay. So it's basically the exponential equations that we're going to be writing for a particular situation. So the next two pages are dealing with specifically, last page was interest, this page is going to be growth. And then the third page, the second half of this video, is going to be decay. Amounts that are decreasing. Here we're talking about amounts that are increasing. So the general formula will be the final amount y is equal to the initial amount y sub 0. So that 0 is a y naught. It's the initial y value. For interest, we call it P, the principal, but here we're not talking about money, so we're not going to call it P, we're going to call it y sub 0. And then E, Euler's number, K to the T, K and T are the exponent on Euler's number E. Okay, so K, T is going to be in time, usually in years, but not always, doesn't have to be. And I think you'll see that when we get to decay, time can be any value we want. We just have to figure out kind of what it is we're going to use. K is sort of like the interest rate. So if you think back into page 1, when we're dealing with interest, like say compounded interest, you can see that this formula is very similar to the formula for growth. So that our K and R are sort of the same thing. It's just that your K is going to depend on the units of time that we use, and also just on the situation that's going on in the problem. Okay, K will be positive when we have growth. So for example, if I put money into an account and it grows over time, it's going to be an exponential growth. And so when we have this situation, K is going to be greater than 0. Okay, and then if we have decay, which we'll get to then on the next page, we're going to get some amount that's decreasing over time. And when this happens, we're approaching an asymptote, as opposed to here, we're sort of getting away from an asymptote. Here, the K value will be less than 0. Okay? All right, so decay when K is a negative. Here we're going to have growth, so the K value will be positive. Okay. All right, so let's do example 1. In 1990, carbon dioxide level in the atmosphere was 353 parts per million. Scientists believe that by the year 2275, the CO2 level will be 2,000 parts per million. Assume that T equals 0 corresponds to the year 1990. So that'll be our starting point. What we want to do first is find our K. So given those two amounts, so in other words, if we look at kind of drawing a picture of this, times 0, that's 1990. We have some amount of carbon monoxide, that's 353, and then at some later date we think it's going to be 2000, and that is the year 2275. Well, that's not the T because our T represents 19, so we would subtract those two. But you see the idea is that we have one point here at the initial time, and then we have a point out here, so that we can kind of find 2 points, and we'll be able to establish sort of what this curve is going to be like. And that curve is, how the curve interacts is going to be based sort of on your K. So this is what we're doing. So if we first have to find K, let's put in, what we know. So we know that our final amount will be 2,000. Our initial amount is 353, both, of course, parts per million. And then E times K and then we'd want to subtract. So really, I guess this would be over here 285 because the year 2027, 2275 is really the year 285 years past 1990. Okay. And so we have everything but our K. We have, the initial amount and the time that it happened, right? 0. And then a final amount at some later time. So those 2 points alone are enough to give us our K. These are the difference in the amounts, and this is the difference in the time. All right, so we'll take, first of all, we want to divide by 353, and we get 2,000 divided by 353. And of course, now we'll take the natural log both sides, and we do natural log because we're using e here. So the natural log of that fraction is equal to, okay, so then this is gone. We have the natural log of this. We bring this exponent using the power rule down in front. We have 285k, and then of course the natural log of e, which natural log of e is just 1, so we can sort of just pretend that that's not there because we're multiplying by 1 and that's not going to affect it. All right, so now what we can do is simply divide by 285. So we get k is equal to the natural log of the ratio 2,000 divided by 353, all that divided by 285. So plug that into your calculator to get our k value. And we know it should be positive because this is increasing, right? Exponentially. It's getting away from the asymptote, essentially. And so that k value is 0.0060857,347. Depending on what calculator you're using, you may not have that many decimal places. Okay. And so now what we want to do is we want to find find the exponential function is really what they're asking to do. So put that back into the equation essentially with your k. So we have the final amount will be the initial amount, which is at the year 1990, which is 353. E to the k, and the k is 0.00608. I'm just going to go out to the 57, and then t. Okay, so if we want to know our final amount at some later date, we can just put that year in, the year since 1990, and we can use our function to calculate it. So in this part, they were just asking us to find that exponential function, and that's it. All right, and then part B says, use your function to estimate the year in which the CO level reaches 560 parts per million. So pause the video and do that. So we know our final amount we want is 560, initial amount 353. E to the k, and that's going to be 0.0060857, and then t. And like how many decimal places you go out to for your k. I mean, it's nice if you can just kind of keep them all in your calculator and recall that. But sometimes that's a little bit harder to do. But if you can do that, that would be great. Okay. We're solving this for t, so we're going to first divide both sides by 353. That leaves us this on the left side. We take the natural log to bring that exponent down in front. So the natural log of this side, the natural log of this stuff, bring that coefficient down in front, 0.0060857 t, and then natural log of e, which we'll ignore. All right, so we can solve that for t by taking the natural log of 560 divided by 353 over 0.0060857. And again, how many decimal places you take out, your answer is going to change a little bit. But, we're going to do it to the nearest whole year. Okay, so plug all that into your calculator. And I think you get 75.8279. And of course, your number will be slightly different if you used a different number of decimal places for your K. So, so that's about 76. So we'll say approximately the year 2066. Okay. All right, let's try an example number 2. According to the U.S. Census Bureau, the world population reached 6 billion people at the beginning of the year 2000. The world population increased to 6.953 billion at the beginning of 2010. Find the exponential function that gives the world population based on years since 2010. I'll let you pause the video, and then if you haven't finished that, pause the video, and then it'll give you a time to write that. So first thing we want to do is find K. Oh, wait a minute. Let's stop and rewrite this. Let's do this as 2000. That probably makes more sense because that's the starting point. So let's do that. Let's not write it in terms of 2010, 2000. I think that's a typo. All right, so now find the exponential function that gives the world population. All right, so we want to find K first. So the final amount will be the later year, 6.953 billion, and that's equal to 6 billion, which was in the year 2000. E to the K, and then we want to think about T, and that's 10 years later. So, this is the difference in the populations, and then this is the difference in the time and years. So, we're going to do 6 divided by 6.953 divided by 6. So, divide both sides by 6, and then take the natural log. Natural log. And we get, 10 times K comes down in front, natural log of E, which we'll ignore. All right, so K is going to be equal to the natural log of 6.953 divide by 6. Sorry, shouldn't really write my fractions like that, but I don't have the space. And then divide all that by 10. All right, so that gives us a K value. Again, it's what's happening. At time 0, it's 6 billion. And then at 10 years later, we're up to, 6.953, right? So we have sort of this curve that's happening here, right? So we're increasing. So, of course, it makes sense that our K is positive. 0.014741375 Again, depending on how many decimal places you got, your next equation might look a little bit differently. All right, so what is our equation then? So our equation should look like y equals 6, because that's the initial amount at 2000, e to the 0.014741. So I'm just using out to 5, 6 decimal places, and then t. So that is our function. And then now let's use that to find when the world population will reach 7.8 billion. All right, so divide both sides by 6. We get 7.8 divided by 6. Again, I'm not going to use my calculator yet for that. I'm moving the 6 over. I'm going to take the log of both sides. I'm going to use the natural log because we have e. So that's 0.014741 t, natural log of e, which we can forget, and then simply divide. So we get natural log 7.8 over 6 divided by the k. So if you saved your k in your calculator from this up here, when you go and plug all this in, you can recall previous answer, and that maybe will get you a slightly different answer. Depends on how many decimal places you use. I tend to use all of them when I recall my calculator. So let's see, I get a t of 17.7978. So we would probably say, well, that's about 18 years. 18 years since 2000. And so that's about the year 2018. Okay. All right, let's move on then to page 3. Page 3 is specifically geared towards decay. So page 2 was looking at growth. Now page 3 is looking at decay. All right. So the same kind of formula, it just means that now what's going to happen is we have some amount, initial amount up here at certain time 0, and then at some future time the amount's going to be less. And so we're going to be looking at a curve that does something like this. Okay, so decay means we're going to have less over time. So this, for this much, k is going to be less than 0 for these problems. Okay. Now, specifically, we'll talk often about half-life, and half-life is a property of biology, physics, chemistry, where half-life of a substance is the amount of time for that substance to lose or decay 50% of its amount that it started with. Okay, so it's a fact of physics and chemistry that everything sort of has a half-life. All right, so paleontologists study life of past geological periods by studying fossil remains. They use carbon-14 to estimate the age of fossils. Carbon-14, which is an isotope of carbon-12, decays with time. So in 5,700 years, just half of the mass of this substance, of this carbon-14, will remain. So if some animal dies, after 5,700 years, the amount of carbon-14 that we would expect to find in a fossil would be half as much. And this is what we would expect if that person or thing had just died. Okay, so Portia, the paleontologist, finds a bone where only 1/50th of its original carbon-14 is left. How old would the bone be? Okay, so the first thing we're around to answer to the nearest 1,000 years. Okay, so this is a model for problem number 24 on the homework, by the way. All right, so the first thing we want to do is find our k, right? We need our k. So what we know is what happens, right? We know that use this half-life information. So we know that if we start with one amount, we have 1/50th at the end, right? So like we found this bone. We don't know how old this bone is, and that's what we're trying to find. But we know that if we start, the animal dies, so we start the clock at time 0, it has some amount. And then we know that 5,700 years later, oh, sorry, I don't want 1/50th in here, sorry. We have 1/2 is left. So this is one half-life, and so that means if I start with 1, half of it is left. So we're not using this 1/50th yet. Okay. So we're using those two known points to find our k, our sort of, remember, think of it as like an interest rate almost, our k value here. So one whole amount becomes half in 5,700 years. And so what will the k be in this situation? All right, so we don't have to divide by 1. We can just sort of ignore it. And then we take the natural log. So the natural log of 1/2, and the natural log of this, we can bring down the 5,700k natural log of e. All right, so our k value will be the natural log of 1/2 over 5,700. All right, and so that value, let me write down below. So k, the constant for this situation, is going to be negative because, like we said, we're decreasing. K is going to be negative. 0.000121604769. Now again, you may not have that many decimal places displayed in your calculator. Just go out to as many as you have. All right, now what we want to use is find our k to find the situation. All right, so now we find a bone that has 1/50th of its original carbon. So that would mean 1/50th of the original amount, E, and I'm just going to write K, but I'm going to use that K value up there, and then T. So this time we're looking for how old the bone is if 1/50th of the carbon 14 is still in it. So we'll take the natural log of both sides. So we have natural log of 1/50. And then that's equal to, let's write it. So negative 0.000121 ... t. And then, of course, we use, the natural log. We brought the kt down in front, natural log of e next to it. So t will be equal to the natural log of 1/50 divided by your k. So negative 0.00012 ... So if you can, after you've calculated this, leave your calculator alone and now pick up your calculator right here. You haven't touched it. You have this still as the previous answer, natural log, and then parentheses 1/50, close the parentheses, then hit divide by, and then previous answer, and then you'll get a t value of 32,169 years, 0.98, let's say. And so what will it be if we're rounding to the nearest 1,000 years? So about 32,000 years old. Okay, so the bone is from something that died about 32,000 years ago. Clearly not a dinosaur. Okay, now, I'm hesitant to even show this to you because this is something that they use in science class, a different version of this formula. It's only really helpful when they give us the half-life. So they gave us, in this case, they gave us a half-life of 5,700 years. This particular formula I'm going to give you is what you use when you're in science class. So the science teachers give you this formula. Y, the final amount, equals the initial amount of y sub 0, and then it's 1/2 1/2 t, the exponent is t over x, where x is the half-life. And the half-life can be in any units you want. I mean, any units that they give you. Like some radioactive isotopes, the half-life is a couple seconds or milliseconds. So it's very quick. Here, our half-life was in years, but half-life can be in any time. Just means the time you put in t and the half-life units have to agree. So t over x is the exponent on the 1/2. Maybe that wasn't super clear the way I wrote that. Okay, so if we were going to use that formula, it would be actually pretty quick in this one because they gave us the half-life. You'll notice in the other examples that we have on this page, we don't give you the half-life. So this form of the equation is useful here because they gave us the half-life. Otherwise, we'll just resort back to our k, be consistent with our other formula that we use in our other situations as well. But in this case, they gave us the half-life, We know the final amount. We know the initial amount. So 1/50th equals the initial amount of 1 unit, whatever that is, 1/2, and then t divided by 5,700. All right, so we would take the log of both sides. This time I'm going to take just the common log because there's no e's in this formula. There's no benefit to taking the natural log. You can certainly take the natural log so long as you do it to both sides. And then when we do this, we have t divided by, we're going to take the log of both sides, and this exponent comes down in front. So t divided by 5,700, and then log of 1/2. So in this case, before we had log of e, we could just ignore it and we don't bother writing it. But here we have to have it. All right, and so now we want to get t by itself. So I'm going to multiply both sides by 5,700, divide both sides by log of 1/2. So t is going to be equal to 5,700 log, common log of 1/50, and then divide all of that by log of 1/2. So just be careful of your parentheses, making sure you close parentheses properly. Plug all that into your calculator. Let's see what you get. I got 32,169.98 years, which is the same as what we got before. So approximately 32,000 years if we're rounding to the nearest 1,000 years. Okay, so we get the same answer in either case. This one's a little bit nicer. You don't have these two steps you have to go through, but really it only works, it's only beneficial to use this form of the equation when you're given the half-life. In the next two examples, they don't specifically give us the half-life, so there's really no benefit to using this. But just, I wanted to show it to you because you will use this form. Science teachers tend to use this form in science class if they do any kind of half-life calculations. All right, number 2. Let's do this one. There's a new element called neunium. Totally fictitious, by the way. And the symbol is Nu380, which decays like carbon-14 but faster. An organism has 4.43 times 10 to the 33 atoms of neunium-380. When it dies 20 minutes later, it has 2.891 times 10 to the 29 atoms of neunium. And the half-life of neunium, find the half-life of neunium and then calculate how many atoms the organism will have after 2 hours. All right, so we want to find our K first. So set up the formula, let's see what you can do with that. So we have, again, we have sort of this situation where at time 0, the organism dies, it has so much. At some later time, 20 minutes later, it has a less amount, right? So it's got this curve. We have these 2 points, so we should be able to find the K for our equation, and then find out how many organisms are left after 2 hours. Okay, so this one's going to be a little tricky because you've got scientific notation going on here. All right, so I have our final amount, 2.891 times 10 to the 29th atoms equals the initial amount, 4.43 times 10 to the 33, e to the k, t. Now, got to be careful here. We have 20 minutes. We've got hours here. So we have to just figure out which one we're going to do. We're going to do minutes or we're going to do hours. Let's go ahead and do minutes. We'll call this 100. When we get to this, we'll call it 120 hours. I think that's probably better. Yeah, it just depends on how you want to do it. You can either put in 1/3, so 20 minutes is 1/3 of an hour. Yeah, let's just do that. All right, so I'm going to put in 1/3 here. All right, so I'm doing everything in hours. That way we can just leave this as 2. It doesn't really matter. Your K will be different if you put in minutes versus hours, but your final amount will be the same. that doesn't matter. Okay, so what we're going to do first is divide these, right? We get 2.891 times 10 to the 29th divided by 4.43 times 10 to the 33rd. Let's just take a second and figure out what this is. I could divide these, and then I can subtract these exponents. So when I do that, I get 0.6526 times 10 to the, I subtract these, I get -4. All right, so I've divided both sides by this stuff. I'm left with e to the k times 1/3. I'll take the natural log of both sides. The natural log of this I can bring down in front my k over 3, natural log of e. And now I just simply multiply it through by 3. So k is equal to 3 times the natural log of 0.6526 times 10 to the -4. And just be careful when you plug this in. This isn't technically in scientific notation. It should be 6.523. I just left what the calculator gave me when I divided these two numbers in front. But you would move that decimal place over if you wanted to and then make that a -5. But it works just the same here. So we get a k value of -28.911 3938. Again, I'm just using as many decimal places as my calculator will give me. All right, and so now let's figure out how many organisms we have, or how many atoms the organism has 2 hours later. So that would be, okay, that's just going to be pure calculator work, right? So the final, not initial, a final amount is going to be our initial amount, 4.43 times 10 to the 33, and then e to the -28.911 3938. And then we want to use a value of 2 here. And then that's just all pure calculator work. Be careful when you hit your E. Make sure you're putting this stuff in parentheses, multiplying those two things. And again, we're using hours, again, 1/3, and we're using 1/3 of an hour for 20 minutes and 2. And so what do we get? We get y is equal to 3.422 times 10 to the 8th. Depending on how your calculator put it out, it may use scientific notation or it might just put it out in regular notation. But it's about 342 million atoms left. Okay. All right. All right. So I'm debating whether I should show you how you could also do that with the other version of the formula. I think I'll skip that one. I mean, sure, feel free to go and try it if you want. Ultimately, I don't care which one you use. I mean, if I ask you to find K on a quiz or a test, then you need to work with our version of it here. But if all I'm asking for is how much you have in your final after 2 hours, then if you feel more comfortable with that formula, it doesn't really matter to me which of the two formulas you use. All right, let's go on to the very last problem then. So at 8 a.m., Gertrude drinks 130 milligrams of caffeine. At midnight, she still has 15.9 milligrams of coffee in her system. How much caffeine was in her system at 2 p.m.? So again, in this case, they didn't give us a half-life. They gave us two amounts, right? So they said, at time 7 a.m., she had so much in her system, And then at midnight, she had, this amount. So we have some kind of curve. Eventually she will approach having 0 amount of milligrams. So it's sort of approaching an asymptote. So it is, again, a negative value. But we can find our K based on those two data values in our graph. All right, so the final amount at midnight was 15.9 milligrams, and she started with 130 at 7 a.m. All right, so E to the K, and then we have to think about how much time. Well, starting at 7, going to midnight, that's 17 hours. Okay, so we just solve this one for K, divide by 130, so we get 15.9 divided by 130. Take the natural log of both sides. Natural log then of this stuff, this coefficient comes down in front. 17K, natural log of E would be left. Again, we're taking the natural log because there's E in this formula. All right, and so then we would just divide. So K is equal to the natural log of 15.9 over 130, divide it, let's put that in parentheses, divide it by 17. And so we get a K value, again, it's going to be negative, 0.123600902. And now it's just pure calculator work. Take that and plug it into the, let's see, how much caffeine's in our system at 2 p.m. So that's asking for the final amount. E to the K, negative 0.123 ... And then what would our T be at 2 p.m.? That would be 7 hours later. Okay, so again, this is just pure calculator work. Take out your calculator, plug that in. I get something like 54.7 milligrams. Okay, so again, you could use the other formula for this. Y equals y sub 0, 1/2 raised to the time divided by the half-life. Use that formula. There's no real benefit. You probably would use the common log rather than the natural log. You could use either one, but you don't have the E in the formula to help you with that. So you'll get the same amount at the end if you use the half-life, this specific half-life formula, rather than just the decay formula that we're using. You don't have to find your K first, but what you would find is your X first. Your first solve for X, that would be your actual half-life. So now that I'm thinking about this last problem, number 2, it did ask find the half-life. We actually did not find the half-life in this one. We could find the half-life using this other formula. Instead of the K, we would find the X. The X is specifically the half-life. So maybe for this one, because they were asking for the half-life, it would have been more direct and easier to use this formula. So up here, to have reused y equals y sub 0, 1/2 raised to the t over x. Remember, x being the half-life. And in this case, you would either use minutes or hours. I think when I went through this in minutes, I think I got a half-life of about 1.43849 minutes. So if you go back and you actually do that, solve this problem, you would put the initial amount here and the final amount here for the time we know, which is 20 minutes. So I would put t in as minutes there, and then solve that for x, and you will get like roughly 1.5 minutes or so. 1.43 minutes is every 1.43 minutes, half of the material goes away. So 2 hours, most of it's gone, right? I mean, you might say, oh, we have 342 million. That seems like a lot. But look at how much we started with. I mean, that's more than a mole, you know, so that's a huge amount. So the amount we have left is minuscule compared to what we started with. All right, so that is page 2, and page 3 of the notes. I'm going to stop this video, and the next video we'll cover page 4, which is Newton's law of heating and cooling. Using the same general formula, we'll use the decay formula for that.